Okay. Alrighty, well, what I want to do today is wrap up our discussion about absolute time. And just a couple more things I want to kind of touch on there. And then I want to start talking about the solar system, where all this came from, and how it formed, what we think are kind of the basic start to planet Earth, and give it some context. And I think that will also give you a little bit of a feeling as to why we keep coming back to this idea of why Earth is old. And we're going to keep kind of hitting on that theme by showing the evidence as we go through the semester. Okay, so if you remember when we talked about time, we said there were two kinds: relative time, just putting things in order, and absolute time, giving it a specific age, a specific date of formation. And that's what we've been talking about here this last time. Now, we talked about how we could do this by looking at the parent-daughter ratios of radioactive isotopes. And knowing the constant rate of decay, the half-life of these isotopes, we could then look at how much daughter we have compared to the beginning parent material, and we could convert that then into the amount of time it's taken for that parent to decay into that daughter, and that way we could put an age date on that rock. And it sounds pretty easy, but actually there's some constraints that we have to obey and assumptions we make that we've really got to be careful about, because it doesn't work for everything, and we have to realize that. And if we're going to have any credibility in using these dates correctly, we've got to use them correctly and use them properly. So here's some of the concerns that we have to be aware of when we're trying to do this age dating. The first thing is that if we're going to do this, this depends on some type of isotopic decay, the natural clock. So that means whatever we're looking at, it's got to have some isotopes in it that we can date. And not everything has isotopes in it. So if it doesn't have isotopes, we can't date it. The other thing is, the process has got to operate at a consistent, a constant, known rate. If the decay rate varies, if it would speed up or it might start fast and slow down, if it varied, we'd never know how long it really took. We wouldn't know where in the process we were as far as the rate of the decay process. So we have to make the assumption that the decay rates of these isotopes are constant. Now, they may be different for different isotopes, but that isotope always decays at a certain rate. And we keep going back and we measure these, and as we get new instrumentation that can measure it in even more decimal places, more accurately, we go back and we redo it. And we're always honing those numbers, getting them better. But what we've been able to see, as long as we've been doing this, with all the lab experimentation, is this holds true. So our dates get a little better as we can measure more accurately, but the idea that it's a constant decay rate for each particular type of isotope appears to be correct. We also assume that we start with no daughter isotopes, that all we start with in the material we're measuring were parent isotopes. What would happen if we got a hold of a rock that, when it formed, it had both parent and daughter isotopes? Well, there would be extra daughter there, wouldn't there? It would mean that there had been more decay going on, and we would get a much older date because it appeared that this decay process had been going on for a lot longer to make that larger amount of daughter. So is it a good assumption to say that there was no daughter in this material? And that is part of what constrains us to looking at certain types of rocks and excluding other types. Because some types of rocks will have some daughter material in it. We can't use those. So we restrict the type of rocks that we age date to those that we know would start with nothing but parent material. So that's going to eliminate a lot of stuff. We also look at this idea that it's a closed system. We don't have daughter material that's coming from outside and it's getting added to the mineral. We don't have extra parent that shows up and changes the ratio. But it's a closed system, and we then have that baseline that we began with that we can compare to. We need to know what the original amount was. And this clock, this isotopic decay, hasn't been reset. Something hasn't changed the date. And metamorphism is one of the big things that does that. Heat and pressure. It changes the minerals.